All right. Hello, everyone. Welcome back. This morning, today I uploaded a video for LSTM um, showcasing the reproduction of this blog post by Andre Karpathy. But this is the blog post I'm talking about the recurrent neural networks. But I think I didn't do a not even decent job. It was a bad job at walking through the code that I wrote last week from scratch and using PyTorch throughout. So I wanted to do it again, doing hands-on coding end to end in this video, and then training that model to basically reproduce the results here. So that's why I'm redoing it. I hope you and I uh, get better at coding LSTM networks and training them, and also I can do a better job at teaching that. So if you come down to this part of the blog post Fun with RNNs, where Andre Kapathi tries to train a LSTM model of some configuration for generating Paul Graham essays, for generating Shakespeare text, for generating Wikipedia, then some algebraic geometry text, and also some Linux code. So basically, I found out some data for a Python code, Paul Graham essays, all concatenated, and there's a Shakespeare data. So these three type of data, I'll try to once we have our modeling and data preparation and generation code ready, we'll use these three um, data set to train our models and see the results. Yeah, so get to it. Let's get back to it. And also, before we start coding, let's look at this diagram that I just drew. So I hope that this would make it clearer to understand how the LSTM works. So basically, this is a single cell. So how it works is, let's look at this left side of vertical diagram right now. This is I'm showing here a multi-layer LSTM network that we want to train. Uh, so basically, this is a cell rolled for all the time steps. So a cell takes xt, which is input at time step t, and another input is the hidden state from the previous time step. So you see it coupling as in and out as loop to the cell particularly, because that's a way of showing it as a all time steps rolled into one. Um, and also along with hidden state, there is a cell state in the LSTM, which I covered in the previous video. So that could be seen to understand more conceptually. So basically I have shown all these operations for LSTM cells. In a LSTM cell, what different operations on xt and ht minus 1 go in place, and ct minus 1 to get the final ht and ct. So I'm not going into it again, but how it's represented here. So first, the lowest layer, the starting first layer of LSTM takes in xt, ht minus 1 and ct minus 1 for this particular layer. The upper script 1 means for first layer, 2 means for second layer, and so on. So it takes in ht minus 1, ct minus 1 as input, and xt for the current time step input, and it does some set of operations and throws out new hidden state and new cell state. Now, the new cell state rolls back and goes into the next time step input, uh, and the new hidden state, it does two things. It goes back as input to the next time step, and also it goes back as input to the same to the cell of this small t time step of the next layer. So this is a sequential operation. So after you have computed the hidden state of this cell, of this layer, then you go on to calculate hidden state of second layer. Basically here xt would be just h1t, which is coming from the first layer hidden state, and we'll compute the new hidden state of second layer and cell state of second layer, which would go on to further h2t will go on to feed into the LSTM of cell of third layer, And once from the final layer, once we have a hidden state, we can use that hidden state to do a linear transformation, which is we are calling as a head, LM head, and it will give us a logit. So this is what a high-level view of LSTM, multi-layer LSTM would look like. But to understand it better, I have drawn it in unrolled format. So where each time step is shown separately, it will be sequentially processed. So at time step 1 or 0, x1 is going in as input. These initialize, so all the initial hidden state and cell state for each of the layers will be initialized as zeros. That will be our initialization method. So once we are taking in the zeros, h10 and h10, all these would be a vector of hidden dimensionality size of all zeros. And with these inputs, it will compute h11 and c11, which is hidden state and cell state for first layer and first time step. Then these things would go as input to second layer, second time step, and so on and so forth. It will compute hidden state for all of the time steps, cell state for all of the time steps. So that is the processing for first layer. Now when we move to second layer, so we'll have to be iterating for each of the layers sequentially. When we'll code, you'll understand that once we have calculated hidden states from all of the time steps for layer 1, we'll pass along these hidden state to layer 2. And again, the cell states from this layer won't be communicated to second layer, but hidden state would be communicated. So this would be input. Hidden state of first layer would be input to hidden state of for LSTM cell of second layer, and two more inputs would be H20, which is hidden state of this particular layer initialized at 0, and C20. This is also initialized as 0. So again, with these inputs feeding into the cells of different time steps of second layer, we'll calculate H21, H22, H23, and H2T. Capital T is the number of time steps that we have, number of tokens or number sequence length maximum that we have in this input. Similarly, so for other layer, it's the same pattern. I hope it's clear now. Uh, so after third layer, when we get the updated, the hidden state from each time step, we'll use those hidden states at each time step to get the logits at each time step. So this will be our input. This logits would be our predicted probability distribution, and using the target indices of targets, basically we'll compute the cross entropy loss at each time step. And so B here is basically when we are for efficiency, when we are using batch of inputs. So for each element in the batch, each sample in the batch, or each example in the batch, this would output would have a vocab size length of logits, and that will give us a b by vocab size tensor in each of these time step, and those all these capital T um, tensors, b by vocab size tensors, capital T, they will be stacked together along the one dimension, so they will become b by t by vocab size, and they will be used to calculate compute loss with the target of b by t shape. We'll see in the coding that part. I hope the processing, the sequence of processing that will happen is clear. So cell states are only shared between the time steps of a single layer. Hidden states are along with the single layer time steps. They are also shared with, as they also propagate as input to the as input to cells of next layer. Yeah, so I hope it is clear. Let's start with the code now. All right, first let's prepare the data. So initially in the last video, last to last video, where I coded single layer LSTM from scratch and RNN from scratch, we manually we were writing code without any class definition, structure for preparing the data, but here let's start formalizing it. So we'll make a text loader class, text loader. So what we need initially is we'll need self.text, self.vocab, self.vocab size, self.s2i, self.i2s, and also we'll need self.encode. Let let's leave that encode right now. What else do we need? Yeah, we'll need to split the data and so on. So let's say while initializing the text loader, we pass a text, we pass where a parameter val split. This is default parameter 0.9, or let's name it as test split, right? So I think we don't need to memorize the text. We need to make the vocab out of the text. It would be nothing but a sorted version of list of set of text. So the set of text will give us all the unique characters in the text. List will make it as a list, and we'll sort them alphabetically or with the along with the characters as well. We take a len of self.vocab, which will give us vocab size. S2i is nothing but a mapping character to index for ch in or I ch in enumerate of self.vocab. This will be a mapping from string characters to indexes. For index to character string, we will reverse it. So I to ch for chi in self dot s2i dot items. So this will give us reverse mapping. Now let's initialize a number which should be um, test split times length of, or maybe let's say we make self dot data equals to mm, a list of self dot s2i. We are converting all the entire text to indexes. S2i of ch for ch in text. For the entire text, we go by each character. Now we are doing character level modeling still. So we pick each character in the text, we convert them into an integer based on this mapping, and we pack all these into a list. So this will be a list. Now we make this number. We take 90% as the split point for this data length. We say self dot trained data equals to self dot data. We index it till n. Self dot val data equals to self dot data and onwards. So we have our train and validation split done here as well already. We have our mappings, we have our data. Now what we can do is we can define what we need is we need an encode function which takes in text and splits, returns list of character indices. We need a decode function which will take in a list of tokens, return a string for the tokens list. And also last thing we need to make is a get batch function. So get a batch of data from the whatever from the train or validation set. Batch size is a parameter I'll take, and block size. So these would be two parameters, right? So let's start with encode function. This should be basically simply you take in text, you encode them into list of integers, which is nothing but simply this. So we can do return this thing. List of the all the indices corresponding to the characters. Then for decode, what we'll return is we'll have to join this list, which would be mm, for I in, or rather token in tokens, self dot I2s of token. We make a list of all the tokens in this token characters, list of characters corresponding to all the elements in this tokens, and join them to return the string. And the get batch, what will happen is we have batch size and block size taking in as input to the get batch function. So we will say data equals to self dot train if split equals to train, else self dot validation. So sorry, my bad. So if our split argument is train, then we take self dot train data, otherwise we take self dot val data. Now let's make a get a list of indices in the length of train data, 0 till length of train data, for as which are equal to batch size numbers. So we'll use this function toss.randint. So what will this will return us is a list of, let's say, 2, 3, 4, 2, 99, 56, 9,000, and so on. So this will return indices of length batch size. So at these indices, we'll start plucking our data that will go as input and h's of length block size. So once we have our indices of batch size length, what we can do is x equals to, we will index into the data from I to I plus block size for I in IX, and let's wrap this all into a list. So for each integer in the IX, let's say it will pick up 2, and from 2 it will slice 2 plus block size characters. So there will be block size length of tensor, it will become this, and it will, all such tensors will be wrapped into a list basically, so it will become a 2D tensor. Similarly, y will be equal to the same thing but shifted to right by 1. So we'll have I plus 1 and I plus 1 here, and it would be same. So basically we'll take a look at what the examples look like. Once we have our x and y, we say return x comma y. I don't think we have to move it to uh, device or something. I think this should be fine now. This text loader class, let's read in a data text equals to or let's say we read in here. What data should we read? Let's say we read Paul Graham essays, right? PGT read mode dot read. Let's print text first 300 characters. No such file or directory. What is the path of this? Copy path. Where are we right now? Oh, sorry. Okay. So I think we have to go back one directory and then do this. Cool. Okay. So we have loaded the text. This is what it looks like. Whatever. Maybe this should put in first UTF. I'm saying UTF-8 because this some characters look weird. Let's see how it comes now with UTF-8 encoding. It's same. Let's just remove this. Or maybe let's say we read this Shakespeare text. This is what it looks like. Alright, first citizen, before we proceed any further, hear me speak. All speak, speak. Cool. So we have loaded our data. Let's stop printing it now. This is our data. We make a data loader. So let's say we say loader is text loader, and inputs we need, all it needs is the text. So once we have given the input, it should work, and we should be able to look at these attributes of the object, of this loader object. Cool. Text loader type of object dot vocab. So this is the vocab. Print. All right. So we're printing all the characters. First character after sorting is /n new line, and let's also print loader dot vocab size. So 65 is the vocab size. Now, so yeah, our loader is ready. Means encode and decode function could be used, and get batch function could also be used. So let's do get batch. Loader dot get batch. We pass a split, which is from train. We batch size, let's say we want 2, and block size we want 8. So we want 2 examples in a batch and 4 time steps in each example. Let's see what it prints out, or it prints or no. Okay, this is not being run. Sorry. Let's say like this, xb and yb equals to this. So now we print xb yb, or rather cool. Okay, I think right now we are not getting this as tensor dot type of xb. That we get as a simple list because we are not wrapping it in tensor. So let's, after this is done, let's do that torch dot tensor, and we make d type as torch dot long, To this also torch dot tensor d type equals to torch, because these are the integers that we want initially, and they will be converted to float in the embedding layer, but for now we want them as integer, so we are taking torch dot long as d type. uh, Now cool, all right, we are getting them as tensors, torch dot tensor. So now let's try to print them. All right, we are printing the tensor now. So this is tensor of shape 2 by 4. This is the input xb, and this is the target for this particular input 2 by 4. So when you see, what does this represent is, when you, the input token is 58, the output will be 1. When input token is 558 and 1, output would be 43. When input is 58, 1 and 43, because with all the dependencies of hidden state passing along in the next time steps, right? When this is the input at current time step, there would be hidden state coming passing through 58 and 1 and many more previous steps if needed. And this would make it as input representing 58, 1 and 43. So at this point, our output would be, the target would be 60. So the logic generated with these three as inputs at this time step, 43 time step, we'll use 60 as target to calculate the logics and so on. So this is a different, another example in the batch, and the targets for that particular batch. Now what we want to interpret this as, the model, it can take in any number of inputs, time steps or tokens from 1 till block size. Block size is a maximum sequence length that a model will be taking as an input. Uh, so yeah, this is how we get a batch. Now we have our input ready. Let's just get to, okay, now let's get to the models. So now, as you saw in this diagram, in the last to last video where we saw RNNs and LSTM from scratch coding, it was single layer of LSTM. So there was only one class needed, which would be able to just iteratively called uh, on the basis of number of time steps, and we can do all the processing. Now here we would need to break all these computations, so we should make LSTM cell as a different class, and this entire network of multiple layers as a different class. So we'll do it that way. So to do that, we'll have a LSTM cell as a class, right? But for now, let's keep it aside. Let's go top bottom. We'll start with the entire network construction first, and then we'll get into deeper into definition of LSTM cell. So we'll say multi-layer LSTM. This class let's define first. To get this class, what we need is, we need vocab size as input. I'll tell you why. Then input embed, then hidden embedding. These are all the dimensionality sizes that we'll need. Then we'll also need dropout. We'll use, let's say we uh, initialize it with default value of 0.5. Do we need anything else? Okay, let's start writing the code, so we'll figure out if we need anything else. So here there would be two different things happening. So this is the network we are constructing. We need to take an input, embed it into some dimensionality. Right now we have integers in the batch by b by t shape tensors, where b is the shape of length of the batch size, and t is the block size or maximum sequence length. So we need to embed in them all of those integers into some embeddings, some let's say 20 dimensional embeddings or 64 dimensional. They feed them into the LSTM cell, and uh, we'll need to initialize whatever is we'll need to initialize these hidden states going into the LSTM cells as well. So let's start making. Yeah, we'll need to initialize these in LSTM cells as a list of modules also. So first is, let's say, embed layer, or we'll just say embedding equals to tos dot tan h tos dot rand. So input shape would be vocab size by input embedding. So this would be a embedding table of vocab size by input embedding. We'll plug the indices row for the corresponding indices from our uh, inputs. I'm going to just wrap all these, or let's let's leave it at that. Or then after embedding, we'll need to initialize all the cells in the layers. Okay, one another value that we need is number of layers, LSTM layers equals to, or maybe should I use this? Okay, so different ways I can do is, we can either initialize as plain list, and then while doing the forward propagation, we'll need to index them, plug them out layer by layer, and do the forward pass. Okay, I think we'll do it this way. We'll wrap all these parameters into an n dot parameter. So this I'm doing because it will automate whatever tensors are added are wrapped into an n dot parameter in the model. It will automatically add them into model dot parameters method, and we won't have to define it separately. And this I'm going to take as initialize as an n dot module list. That would be easier to forward propagate later. If for layer in range layers, or let's not do it this way, self.lstm layers.append initial, the first layer would be LSTM cell of, will pass in input embedding and hidden embedding. For layer in range, for other layers second onwards, 1 till layers self.lstm layers.append LSTM cell of hidden dimension by hidden dimension. So we are appending these many layers. First one is of this shape, input dimension by hidden dimension, because you remember from our diagram, the input going into the first is different. It is of this xt shape, what is the input dimensionality it is. It can have the same number as hidden dimension, but it can also have different. Therefore, we are separately appending it. And next layer onwards, the inputs would be of same dimensionality as the hidden state outputs. So yeah, we have added the layers. Now, after all the layers, we'll have self dot uh, head, which would be an dot parameter dodge dot rand. This would be hidden size by vocab size. So here we'll be transforming from hidden dimensionality, each hidden vector from each time step to vector of shape vocab size to get the logits. Mm. We'll also need to incorporate dropout. So let's say we'll say that self dot dropout equals to nn dot dropout, and this will happen only if dropout is not none and layers is more than one. So only when the number of layers is more than one, then only we'll be applying dropouts here between the layers. Otherwise, we don't need the dropout. So that is another condition. And layers is greater than one, else we'll not do dropout. This is the head, and yeah, I think we are done with the. Okay, so now we have defined our initialized our multi-layer LSTM. Now to get this, let's also do initialization to the LSTM cell. So here we'll need, we are taking in these two inputs, input dimension and hidden embeddings, right? So just say the same things. Input embedding, hidden embedding, and one thing we'll also need, you see here, is every LSTM cell is taking in an input, having a output dimensionality, and also taking hidden state from the previous cell, right? So yes, so we'll also have to pass along the hidden state, hidden vector for each cell for the next layer. So we'll also need a cell state we don't need, so state previous. So previous layer, or we'll just say previous layer hidden state. I'm not sure if that is a good naming convention. Previous layer hidden state. All right, so now, or maybe this previous layer hidden state should be given in the forward function. Yeah, when we call this function, let's leave it here now. Self dot. Okay, so here we'll have to initialize the weights for the operations going on within a LSTM cell. So did it go? Sorry. Yeah, there would be. So it's a set of 4 different weights and biases, 1, 2, 3, 4, that you'll need for get gate, input gate, cell candidate gate, and output gate to do all these operations. Previously what we did is, if you look in this file, I've left it open. So after embedding is done, what we are doing is for each particular cell, this is a single cell of LSTM, we are defining one set of weights and biases for input, for hidden input and bias. Then another set, similarly, four sets are being defined, 1, 2, 3, 4, for four different gates, for get gate, input gate, cell gate, and output gate. This is okay, but there's a better way of doing it, that because end of the day, all it does is, if you look in the forward function, it does a lot of matrix multiplication and addition with the broadcasting. Here, it's a lot of multiplication going on. So if we can collapse all these multiplications into one big matrix multiply, it would be better. So let's say here, um, W X gates and W H gates and B gates. These would be three parameters we define, which would mean it's a concatenated version of WXXF. How do I represent this? Or let me say WXF, WXI. No, this is not a good way. Sorry, bear with me. WXF, WXI, WXG, WXO. Let me write it down, then I'll talk about them. What does it mean? WHF, WHI, WHG, WXO. This would be BF, BI, BG, BO. All right. So these are four weight matrices we initialized. Let me do it this way. Okay, so look here. These were the four different matrices we initialized for transforming X to F, X to I, X to G, X to O. So these are the operation on X inputs for at any time step for a particular cell, and it would be done with a linear combination by this matrix. So the size of this matrix for any particular cell is same across all XF, XI, XG, XO. It is n embed by hidden dimension, n embed by hidden dimension. So why not we concatenate all these by making n embed by 4 times hidden dimension? So they would be stacked horizontally, and they would just be, we'll need to take equal partitions of it, 4 different partitions, and it would represent us these 4 different matrices. Or after we do a matrix multiply, uh, this matrix multiply, these 4 matrix multiply, 1, 2, 3, and 4. These 4 matrix multiplies could be done at single shot by a big larger matrix multiply. Let's see how it can be done. So let's define here self dot wx gates equals to nn dot parameter dot rand n. So input to this would be input embedding by hidden embedding times 4. So this is all we have to do to wrap this into a bigger, longer horizontal matrix, and we'll see how the forward propagation would give us same thing which we are doing here in multiple steps. This entire big matrix would give us all these matrix multiply results in one shot, and it would be much more efficient. Let's define WH, initialize this weight parameter torch dot rand hidden dimension by hidden dimension, it would also be multiplied by 4. Self dot bh or b gates equals to n dot parameter torch dot zeros of this size. So you see, after this would transform our x's input to the each cell into hidden dimensional vector. Each sample would be transformed to hidden dimension embedding vector, but there will be 4 such hidden dimension embedding vectors. So it would be feeding into 4 such vectors, would be feeding into this gate, second gate, third gate, fourth gate. So we'll have to chunk it at equal of equal sizes and then use it for 4 different purposes. And similarly, WH gates will be transforming the previous time step hidden state that's coming into as input into that cell into the new hidden state of this hidden dimension. That is also done for 4 different gates, 1, 2, 3, 4, and same for the biases. Once we have all these 3 things defined, do we need anything more? I don't think so. Okay. So we would need one more thing here which we have not added, and this way of doing head is not correct. We would have to have WHY and BY to compute the logits. So basically I'll say WHY and self dot BY and dot parameter torch dot zeros of shape vocab size. So these two parameters would help us, tensors would help us evaluate our logits. And here we have initialized all the 3 weights and biases that we need. So now we can go ahead and write the call function for both these classes. So these call functions would be used when we pass the inputs to these objects of these classes to do a forward propagation. So let's do with the higher level for multi-layer LSTM what it would look like. So for this we would need hidden states and cell states to be initialized as 0 for each layer, and then we would start computing all the operations within each cell. So hidden state and cell state will have length of first dimension would be number of layers, right? So let's write that. Okay, I took a short break. Let's get back to it now. So we first define the forward function or forward pass for multi-layer LSTM. So what we need here is we need HS and CS. This would be torch dot zeros of shape B by T. Okay, so B by T we have to unwrap from X because our X is always of shape batch by time steps. So it would be X dot shape. So this we can initialize like this, and also the same for cell states. Okay, let's close this now and move to it here. All right, so we have initialized our hidden states for each layer. sorry. So for time step, we won't need this because there would be only one hidden state and one cell state at for each layer, which would be propagating for each time step. And we won't have hidden state for separate time steps. We would just keep propagating and keep using the hidden states at every for every element in the batch for each layer, obviously. So this thing for each layer we have to wrap this into number of times in range layers, self dot layers, right? I think instead of this, what we have to do is first let's change this self dot layers equals to layers, and let's do it a different way. So we are taking torch dot zeros of the shape self dot layers by B, and for each sample in B we'll have self dot hidden embedding. Yeah, so we'll have these of shape number of layers by B by self hidden dimension. So I think it's pretty obvious that for each layer and each sample in the batch will have a hidden dimension embedding. There's no time dimensionality here because we'll keep updating these hidden states, and it would be same for cell state as well. Okay. And also let's so for training with the GPUs or MacBook MPS device, we'll need to initialize at x dot device. Cool. So we have our initial hidden states and cell states. Now what we need to do is we'll embedding is self dot embedding call to x. So we pluck out the corresponding rows from the which relate to the integers or token IDs in the x, and we get this would be giving us b by t by um, this is transforming us to input embed shape. So this would be the shape of embeddings. Now, so what we need to do is we need to uh, run these layer uh, each for every time step. So for t in range capital T, we'll need to do something here, and therefore layer in self dot layers we need to do something. So first, for first time step, what we need to do is we need to input xt is equal to um, embedding indexed for each element in the batch. We take tth time step and each embedding in the dimensions. So this would become nothing but a tensor of b by input embed. So because we are indexing here, this would get squeezed out of the tensor shape, this dimension. We are taking just one size there. or let's say this is of B by T by input embed. So we are getting this of B by input embed. Yeah. Okay. Now once we have our input ready, what we need to do is we need to give the input and hidden and cell state, do the processing inside this cell, first cell, right? So let's pluck out the dot LSTM layer. We pluck out the first layer or whatever this indicates, this ID, this index. We pluck out the cell layer. We pass on the, we do it like cell layer. We pass along xt to it. Then we pass along hs and cs. So you see this is taking input as x at this time step and h0 and c0 from previous prime time step. So we need these three inputs into it. Now this, let's also index into h cell and c cell equals to h's of layer and cs of layer. So we pluck out the h and c for this particular layer. So you see there's an additional dimensionality we have initialized it with layers. So we pluck the that for that particular layer, which is defined by this iterator here. We get the h of h and c hidden and cell state for that particular layer at that time step, and then we get the layer module basically here, and we pass along the h underscore cell and c underscore cell, and this we want this to give us a new hidden state and cell state. So h new c new should be received by this, and this basically this layer is nothing but the module of LSTM cell, because you see in this LSTM layers that we are iterating, that we are indexing into here, is a object of this type LSTM cell. So this would be used, this method would be used when we define the forward function for this. So once we have received h new c new, we'll have to pass along this h to the cell, to the input for the next layer. And the c would be propagated to the next time step. I think we'll also initialize a few more variables, hs new and cs new, which would be same as torch dot zeros like of hs, and this would be same as of same shape as zeros like of cs, and these we would use to keep track of the hidden states for and cell states for each layer. hs underscore new for layer this equals to h underscore new, and cs new for this layer would be c new. Yeah, once we have this, so right now what we have is hidden states coming out of this first cell. Now we need to see if there is any dropout applicable between these. So if we have more than one layers and if we have any dropout initialization done of this class, then we use this. Now we say if self dot dropout, or if we say if layer is greater than 0 and self dot dropout, only then we update hs new, or rather h new equals to self dot dropout of h new. If not, else. Okay, sorry, my bad. I think what we have to do here is if layer is less than self dot layers minus 1, if we are not at the last layer from 0 till second last layer, and self dot dropout is not none, then let's rename this as xt, because this becomes input to the next cell. This become, after dropout, this becomes input to the next layer cell, and if we don't have to apply dropout, then if any of these cases don't meet, we just say xt is equal to h new. Yeah, cell states and new cell states and hidden state remain the same. They don't get affected by the dropout applicability. Okay, so now we have xt defined, which would be the input going into the next layer cell. So once we have this, for next layer, once all these operations are completed for the next layer, we would go ahead and get the h and c cell from the initialized value of these two tensors. Basically here we would we would define call the cell forward function of the forward pass of the cell, this particular second layer. We'll get our hidden states from this layer plugged out, and then basically updated based on this. These two will get passed into the as arguments for forward pass for this cell, and we just return the we update the new hidden and cell states for this particular layer into this dummy variable that we have created here. That would be just a placeholder for keeping the hidden cell states for each layers for each element in the batch for now. And once for all the layers we are done, we will replace it for 0th time step. We'll replace hs equals to hs new and cs equals to cs new. So once this one first time step is completed, we would have all the hidden states, cell states in hs and cs, and we'll have the last hidden state to get the logit. So after all of the hidden states, all of the time steps are calculated, should have hidden state cell states at each times, or I think we need to calculate logits as well here. So let's initialize logits as an empty tensor. And after we have the hidden cell states, what we have to do is, for one particular time step, once we have all the hidden cell states updated for all of the layers, we'll have to create the logits. So what we do is YT is, so to do that we need the hidden state from last layer and apply linear transformation on it. Yes, so we take HS of -1, this is input, matrix multiply with self dot WHY and added with self dot BY. So this would give us a logit. This would be of shape B by vocab size. And what we do here is we do logits dot append YT. So at for every time step we incrementally go for cell in each layer, we compute all the hidden cell states, we at each layer we see if dropout is applicable, we uh, uh, drop out the cell hidden state computed here, and we get the new input for the next layer. And also we move these two hidden and cell states for this particular layer into a dummy variable that we have placeholder variable here, hs new cs new. So this would be updated into hs and chs after each layer is completed, or rather after all of the layers are completed, we have updated hs new layer, which is yes. So once all of the layer operation are completed, we reassign HS new and CS new to HS and CS, and we update compute YT with this matrix multiply and bias addition. This is the last layer hidden vector that we have for each sample. So we get this. This would be basically B by hidden dimension size, and WHY is hidden dimension transform to vocab size. So this would give us B by vocab size, and we do a broadcast addition with vocab size of bias, so we get B by vocab size. Now we keep appending logits YTs to logits. So there would be total of capital T logits, capital T elements in the logits. Uh, Now, so one iteration of these two loops together would basically, or sorry, one iteration of this particular loop of a layer of all the layers would give us a computation for first time step for all these three layers, for all these three cells. And in the end, we have new hidden state, new cell state for each layer to propagate to the second time step. And we also have computed logits for this particular time step. So the target at this time step would be used to compute the loss. We have the logits, and by end of it, we'll, yeah, so we'll have all these. So now all we have to do is we have to properly arrange logits. So right now it is kind of a uh, now logits is of shape T, or rather say T by B. Let's say it this way: T elements in of shape B by vocab size. So what we do is we stack all the elements, because this was a simple list, you remember we initialized, so we need to make this as tensor. We stack all the T elements in logits with dimension 1. So what this will do is this will just basically give us a tensor of shape B by T by vocab size, and this would be what we need to calculate the loss. we return logits. We can also return HS, but we'll see that later if we need it. Okay, I think this pass has a forward pass for the entire network. Now we'll need to define the forward pass for each cell, what's going on in between there. Okay, now let's move on to define the call function, complete the operations that are happening here. So here we are passing, what are we passing here? This is the thing that's going on. So we need an input xt, we need a h cell and c cell here. So input going in is of shape b by input dimension. So we'll just say x here is of shape b by hidden dimension, or sorry, input dimension. Yeah. So it would not be input dimension at every time. For after once we are calculating this here, second layer onwards, it would be hidden dimension. So we can just say it something like n. So what do we have here? For every cell, we will get hidden state from here and cell state from here. So we basically need H and C, hidden and cell state, coming in here. So let's call it hidden for that particular layer and cell for layer. Yeah. Now we have X hidden layer, hidden dimension layer, hidden and layer cell. So what we have to do is we have to first compute the projection from these gates. So this is layer, hidden is of shape b by hidden embed, and it's also the same for layer cell state as well. So we get first operation is x gates, h gates. So x gates is nothing but x matrix multiplied with self dot w x gates, and h gates is layer hidden matrix multiplied with self dot wh gates. So you see here, this is basically b by h matrix multiplied with input embed by hidden embed. So this would give us, or rather b by h is nothing but b by input dimension for that particular layer. This will give us output as b by hidden dimension, hidden embed. Yeah, and this would give us, this is b by hidden embed matrix multiplied with input uh, hidden embed by hidden embed. So this should give us b by hidden embed. Yeah. So this is what's going on in here. We get these two vectors now. So gates output is equal to x gates plus h gates plus self dot b underscore gates. So this is the calculation that basically is happening here. If you see these three matrix multiplication, two matrix multiplication and addition with bias is similar to what we are doing now, but we are doing all of these four version of these three calculations altogether. So basically this is all wrapped up in here. This would give us um, so this here basically is times 4 dimension. This is times 4 columns. Yeah, this here is times 4, so we get times 4 here. So these four different, all these computations are stacked into one big matrix and we'll have to pluck out of it. So we'll pluck out ft, it, gt and ot out of it. We call dot chunk to it and we call four different matrices will chunk out of it along dimension 1. So along the columns it will break it up into four equal parts and it will give us outputs for get gate, input gate, gt, ot. So basically if I show this here in a one particular cell, what we are achieving now with that chunk is we are getting ft, it, gt, ot, all that we need to compute a new ht and ct. So that's what happened here with this single line, basically four lines of operations. And once we have all these, we can update our ht or layer hidden and layer cell. I feel like this naming is really bad, so let me say h previous and c previous. We give this here x gates. I'm not sure if c previous would even be used next layer because it is going to the next time step, right? So if you see here, what's happening is when we are calling each layer, cells in each layer, we have to propagate hidden state from the previous layer as a new input with dropout, but the cell state has to go to the next time step. Yes. So the cell state that we are passing here right now is basically in this function, it's C cell. So for this particular cell, whatever cell we have calculated, we have passed along for this current layer, whatever hidden and cell state we had right now, we have used it to calculate C cell and C new. So we have passed that cell state to this particular cell to compute new cells, right? These two, these two will enter it. So let me go back to the diagram. I'm a bit confused here. So what's happening is we've taken these two hidden and cell states, we compute all the do all the operations, we get these new versions of it in cell state. And these two we are updating to the that particular layer hidden in cell state in HS new and CS new. So we have updated it. Now we have updated this with H new and C new here. Now we have also used H new to compute the new input XT, which goes in as uh, which will basically updated as xt. So when we call the cell layer next time, we'll be passing the xt, updated xt, and we'll be passing h cell, c cell, which will be hidden in cell representation for that particular next layer. Let's say initially initialized to 0 next time. Yeah, so I think we are doing it correct. Um, let me h at, now we need to calculate h at time step t, which is something, c at time step t, which is something. First we should calculate c because c is used to calculate t also then. So what happens here is c at time step t is ft times c rev plus, let's copy paste this entire formula, write it here, ft times c prev it times gt, and ht is, let's copy the formula for this also. We do it this way. Here we'll use the current time step cell state. So we have computed our cell state and hidden state with the as per the correct operations. Now what we have to do is return, we have to return what? This should return h new and c new. So basically we just return ht and ct, and this should be all right now, I think. Mm, okay, I think this looks all right. So basically, once we call this on a particular layer, we pass the input, hidden, and cell state for that particular layer. Or rather, let's say I should call this hidden state for this layer and layer. That would be better naming convention, I think. We pass these here, so it's easier to understand, I think. And with this layer we get new after this forward propagation, forward prop, we get new hidden and cell states which we assign to this placeholder variable, uh, and after all of this is done, all of this one iteration for all the layers is done, we update hs with hs new and cs new correspondingly, then we restart. Okay, so these two things shouldn't be initialized here. They should be initialized somewhere here, I believe. Yeah, because if we are initializing here and we are reassigning it, so for every time step this will get initialized to 0. That doesn't make sense. So basically these two things, HS and CS, should be initialized here. Yes. All right, let's bring this down. Uh, Sorry, my bad. These two things still should be at the same place because HS and CS anyways we are doing correctly. We are initializing here at this point. We should have this placeholder variable to be assigned for every time step. This actual hidden cell states we are not initializing every time. Huh, cool. Mm, let's also add device here, x dot device. Or we can also say self dot hs dot device. Device equals to cs dot device. Yeah, should be okay. They move to that particular device, and then we can, yeah, or maybe calling it as x also should be okay. Or xt dot device, xt dot device. Cool. So I think we have a network ready. I'll take a break and I'll come back and work on the training part of it. We'll also have to do some uh, training preparation, so we'll work on it. Okay, so I just I initialized the model that we wrote and printed the number of parameters. So input representation dimensionality, I took it as n8. Hidden size I took as 32. So initialize the multi-layer LSTM with vocab size, input embed, hidden embed, and layers equals to 2. True, 2. So we are printing a number of parameters which is coming out to be 16,233. Just looking into the model type, model is multi-layer LSTM. If we look into the named parameters of model, we can see that we get embedding of size 65 by 8. 65 is a vocab size. It is transforming it into 8-dimensional embeddings, each of the tokens or characters. WHY, W and DY is hidden dimension by vocab size. It is because it is the head for getting the logits, and this is a 65 dimensional bias. Then LSTMs, we have two layers, first layer parameters, second layer parameters. First layer input is 8-dimensional vector because it is a first layer, and hidden dimension is 32 times 4 because we are concatenating horizontally all of the matrices for all gates. This is also 32 times 2. This is the bias. For second layer, input size is 32 for both X and H. So yeah, our layers look good. Um so model is initialized. Now we can just, let's uh, remove these things. Now once we have the model, we can try to write a training loop. So let's say for alter and range, let's say we say 2000. What we do is first we get batch of data dot get batch train, and batch size is equal to, let's say we do 8, and block size we do 8 as well. Or maybe this we can start with 4 and 8, right? We don't need anything more. XB, we move these to YB equals to XB dot to device. Rather, let's say I will call them only X and Y's. XY equals to X dot to device, Y dot to device. To do this, or we need to define a, or maybe we'll define a device here. Now I'm training this on a MacBook. I'm trying to train this on MacBook, so I'm using MPS as the device. Model dot to device. Moved model to device. Moved inputs to device. Now I'll get logits equals to model and pass X to it. So this model will take only X as input. Yeah, and once we have logits, we can calculate loss as f dot cross entropy. Now, because logits is of shape b by t by vocab size and y will be of shape b by t. So as per the nomenclature of cross entropy, I have discussed this in previous videos, but we'll have to reshape this of size. Let's say we unpack b by t equals to x dot shape. Yeah. So the first dimension will be b prime c, second will be -1, and y also needs to be changed, viewed differently, which would be b times t, a single vector of b times t size, and there's nothing to ignore. So yeah, we get the loss. Now, once we have the loss, we need to say, okay, before this, what we should do is we should also decide as an optimizer, or let's say optim is equal to first dot optim dot, I'm going to use just random w model dot parameters learning rate. I'll decide it to be, because this is a small model, and I'll just say 1e minus 2 for now, 0.01. Okay, so now we have the loss. Mm, Here we should also have done for p in model dot parameters p dot requires grad equals to true. Now here we'll have to say p dot, so we'll have to say p dot grad equals to 0 the grads, and then we call loss dot backward for backward pass, and we do optim dot step. This is a forward pass, backward pass, update weights. Once you have updated weights, once you have calculated loss here, let's say if at every 100th instance we'll put something to percentage, let's say 200 equals to 0. So last 4 digits decimal places, we are printing the loss. This will be a tensor, so we are taking it as dot item, and this should basically run the optimization. Let's see. Fingers crossed. All right, loss is increasing. I don't know what's happening. Something's really bad. Okay, let's stop it. I think one thing is initialization we have done with random numbers. So let's do it this way, that we uh, multiply it with a small number. so that at initialization all our weights are very small so that our initial loss doesn't get very high. So we'll get a good starting point that way. Now, this is not exactly timing initialization kind of thing, but it is close to it because it's basically scaling down the weights to closer to zero. Okay, now let's see what happens here. Okay, cool. So we are starting at a loss of 4.17. Let's stop this and see. So is this a good loss to start with or not? So basically, we are doing cross entropy, which is nothing but a negative log likelihood. So because we have a vocab size of 65, so each character occurring initially should be uh, a uniform probability. Ideally, probability should be uniformly diffused, so it should be 1 by 65 for every character, and we take log of it and we do a negative. So it is 4.1743. So this is quite, we are exactly at a very good point then, 4.1744. Now, we are able to do it because I just directly multiplied most of the initializations of weights with a 0.01. So we scaled down the weight parameters. Uh, Mostly generally in PyTorch, this is by default done when you initialize any module. When you will do something like nn dot linear instead of toss dot random, it would be internally done using timing initialization. Now, timing initialization method we have discussed in a previous one of the previous videos, so I won't go into it. But yeah, uh, some with that scaling down of weights, we are able to start at a very good point. So this initial loss of 4.1745 is exactly what we want. Um, Let me just put all of this code here. Let's scale up these parameters to maybe let's say 32 and 128, right? Or let's say we'll put 64 to this. Let's say how fast we go train. 22 lakh 42,000 parameters. That's a lot. Okay, let's run this. One a couple of more things we'll have to add to it is early stopping, uh, printing of validation loss, and obviously, yeah, early stopping will be done on the basis of validation loss only. And yeah, okay, let's run this for a while. Okay, so right now we are not able to do much improvement with 2000 iteration in the train loss. We started well. This is a good loss to start with. And we reduced for initial 200 iterations, then we started wandering around the same ballpark. So maybe I think the learning rate is too high. It is oscillating. So let's say if we do, let's, for this purposes, I'll just do 32 and 32 shape of hidden and embedding dimensions, input embeddings, so that I'm able to get results faster. Okay, now we are improving, but pretty slow. Hmm. Although we have, okay, I guess let's just increase this up 128 by 128, and batch size, let's increase batch size to maybe 8, and block size to, we need to increase a context size. That should help a lot to, let's say, 32, but that would just hamper our, let's say, 8 is, or maybe 16 is our block size. This we reduce it to 4. Let's see what happens. 2,79,000. That's a lot of parameters. I hope we reduce well now. Mm, we are reducing. We are reducing the loss. It's slow. Maybe slow is a relative term, so not a good thing to uh, judge it with. Yeah, 3.60, then 3.6. Okay, we have made a big mistake while writing our classes. Uh, so I want to rectify that. You see where we take the chunk the output of the gates output into these 4 variables. We need to, before going ahead and calculating CTHT, we need to do uh, gate operations on these. Ft will be torch dot sigmoid of Ft. It will be torch dot sigmoid of Ft. Gt will be torch dot tanh of Gt. This would be It, and Ot will be torch dot tan sigmoid of Ot. This Ft will get multiplied with C previous, and a product of Gt and It will be added to it. Yeah, so this was a major blunder I was doing. I'll append this snippet of video into that part where we are defining the model, so it would be better. Now let's try to run. See, without doing that, we are able to somehow reach only till the best validation score of 3.55. Let's take it for a spin now. Okay, so in last version of the code, I was trying to train my self-written LSTM network with a text loader and some training subroutine. So I was able to train it, um, but I wasn't getting very good generation. The training was happening with reduction in the losses in the validation set, but I wasn't getting any coherent text or any sensible text. So I went on to read more about how to train LSTM networks. So a few basic differences I found in what I was doing and what is the norm generally in different LSTM based recurrent neural networks based paper, and also some initial methods of training from PyTorch. So I've made those changes. I put that model after the changes to train on Kaggle GPUs, and with around 1 hour of training, I was able to get some decent generation. So let me first show the generation that I'm getting here. No, I'm not generating very vast generation out of this model, just to show. So do not of I may be wife of hereby, shall I not. So basically we see that it has started making words and started to look like Shakespeare text with different characters conversation. Let's take a look at what were the changes that were needed to do. The training routine looks mostly the same as we developed. Generate code, I'll come back to next. It is more or less very similar to what we were doing in our initial videos of using bigram approach by counting by neural networks or using GPT kind of model to generate text. So here in our main classes, what's going on is text loader is mainly the same, what we developed. I'm moving X and Y to devices before returning. LSTM cell, there are few differences. There's two bias instead of one that we were earlier using. So we were using single bias addition happening after at this point, but instead here what we do is for X and H transformation, we are using different biases and adding in the respective steps. Then next differences in all our weight matrices initialization. You remember if we were initializing everything as torch dot zeros and multiplying with some scaling number by 0.01 or something. But from what I read, that uh, most prevalent technique of initializing in LSTMs is this, using Javier or Kaiming normal or uniform initialization for the weight of X transforming into H hidden state, and orthogonal way of transforming hidden states into hidden states weights. So the this basically is a general initialization method in most of the neural networks now, is a Weir or Kaiming kind of uniform or normal initialization. But this is something very specific, I think, to recurrent neural networks. So when this comes from a couple of blog posts or papers, so let me show it. Uh, Yeah, so you see this tos.nn.init orthogonal. So that says uh, described in exact solutions to the nonlinear dynamics of learning in deep linear neural networks. This is the one of the paper that introduced this idea of initializing the hidden state to hidden state with orthogonal weight metrics. Mm. Also, this was also this idea was also talked about in this paper that I tried to read. I didn't. I'm not. I won't be able to get into the details so much as of it. I have not yet understood maybe, but just because this is the norm, I tried replacing my initialization, which was very naive way of initializing weights, right? These days. Um, so it just said that initializing trick in this paper. So this paper is from Google. You see Geoffrey Hinton and Coke Wheatley are some renowned authors. Um, so you see it says uh, we initialize the, so this is talking about recurrent neural networks with ReLU units. That is not as much relatable to us, but it says that initialize the recurrent weight matrix to be the identity matrix, which is orthogonal thing that we are using. Somewhere it talks about Okay, so I don't think I would be able to explain the papers properly, but I referred, I requested to understand it from ChatGPT. So what it says basically is orthogonal matrices preserve vector norms of the matrices that we are initializing, meaning repeated multiplication doesn't cause vanishing or exploding activations, a key property of training LSTMs. It helps maintaining gradient flow over time. This concept traces back to these theoretical works. This is one of the paper where they study the learning dynamics in deep networks. So orthogonal initialization helps to stabilize deep networks training. Basically, that's what they say. And uh, also, next thing is uh, along with this initialization, there is one more additional thing we are doing is we are you see how biases are initialized to zeros, but the first section of the biases, which is for forget gate, is changed to 1. So this is being done because initially uh, if you remember that the forget gate is the deciding factor because it uses sigmoid, so output of this would be between 0 and 1, and this will decide how much of cell state last information from last cell state is carried forward uh, after the forget gate is filtering information from cell state because they are getting multiplied here, right? They are getting multiplied here. So this thing is between 0 and 1. So initially, if we initialize all the biases with 0, it is likely that with small amount of a small quantity of weights or small size of weights, most of the lot of information from the previous cell state might get filtered out or dropped at the initially only. That's why for the forget gates we initialize the biases as 1 so that they can try at initialization they can try to keep most of the information from the current cell state from the previous cell state, and this operation would get most of the as much possible values from cpref propagated along, and this would decide what extra information to be added. That's why this is done at initialization. Then what other changes do we do is um, initialization has changed um, drastically. Then we, instead of using uh, toss.randn here for embedding layer, we are using nn.embedding now. Then okay, so we are also tying weights between input embedding and between uh, embedding and the head, the LM head, that the in the end it converts to um, logits. So basically, if input embedding and hidden dimension is same, so you see how, uh, let me type something here so that it's easier to understand. Uh, Embedding size is vocab size by input embed, and head shape is hidden embed by vocab size. So you see how these two, if input embedding and hidden embedding are equal, they would just become of the same size matrix, just transpose of each other. So these two things are also notionally and intuitively they are kind of similar, because in the input we are transforming integers into some dimensionalities representation for each character, each token in the vocabulary, and at the output side, at the last layer, we are again transforming the hidden dimension embeddings from each from each character into multiple different vocab sizes. So they kind of most notionally represent similar thing. Uh, I'll talk more about them in the GPT-2 work that we are going to further do after this, because it's also being used there. So yeah, this that's why these two, instead of using these two different matrices, weight matrix for embeddings and head, we use the same matrix if hidden dimension and input dimension are equal, and we can just reduce the number of computations that a model does, and also it's better to learn representations this way. So if tie weights is a new parameter that we take is true, and input dimension embedding is equals to hidden embedding, we use tie weight, self dot tie weight. So at the forward pass, you will see that we take the last layer from H, and now when we are calculating logits, if this is true, we calculate it with embedding dot weight dot t. We transpose it, the weight dot t here, because those two weights are of different dimensionality, as I have shown just now. So, and add the bias to it. If it's not, then it's normal. We'll initialize a WHY parameter and use it. So yeah, these are the only changes. Then I added a generate function to it, where we take model mappings, block size, any prompt is given on our device, max new tokens, outpath, etc. to generate. Now here we are, I'm trying to generate from scratch, not giving any prompt. So index would be tos.tensor of zeros, which would become 1 by t shape of tensor, because our model will take b by t shape of tensors as input, right? Therefore, that's what I'll do. And then we crop the last for generating every new token. We are trying to generate 500 new tokens. So I'll crop the last block size sequences, last block size time steps from the IDX. We give it to, because a model takes maximum capital T time steps, which is block size. So we do that. Um, Model, we do a forward propagation. We get the logits. From logits we take last time step, which would be, because last time step will be used to get the logits for that particular input, for that block size input. Get probabilities. We get sample from using multinomial, append uh, a string corresponding to this new IDX to our generated characters. Then next index tensor is uh, basically a tensor version of this, and we concatenate IDX next ID tensor. So we update IDX with adding on next IDs at every time step, at every max new token step. And once we are done with all the 500 new token generation, characters generation, we join them all together to make full text and print it. So this model we trained with 384 dimensional embedding input size and hidden size. Batch size is 64, 182 block size. Two layers drop out of 0.3. Our model was able to 2.3 million parameters model was able to go till 1.60 validation accurate validation loss, and I just interrupted at this point because I wanted to not invest more time, but because I thought it would give decent generation, and it did. So it does start giving something sensible. So I thought, yeah, those changes that I made after reading out those blogs and these blogs. So there are a few blog posts, pretty old, which talk about defining the weights this way. And there are research papers that also talk about the initialization in recurrent neural networks is of importance to train it with some stability. And also, yeah, so those were the changes with which I was able to train my model uh, to a decent extent. Also, obviously, if we scale these up, it maybe I'll be able to do better. But one problem still lingers around is this model that I wrote myself with some new updates for initialization. This even I scale it up to 512 or 1024 hidden dimension sizes, and with more layers, etc. It is not able to utilize the um, 15 GB GPU that I'm using with Kaggle to the fully. It maximum goes on to take 2-3 GBs of it. But whereas the code that okay, so after this, what I did is wrote a, I use this code. This is an old code that I wrote a couple of days back. So you see this class, and this is the character LSTM where you will see me building multi-layer LSTM simply very easily out of using nn.lstm. So you just give it hidden embedding, input embedding size, hidden size, number of layers, and it will just generate a network for you. And forward pass is also simplified very easily. Generate function is same as our previous one. But yeah, that's all it takes to build a LSTM with using all torch functionalities. And this network was very easily able to get me results that you will see here in the generations, which are also of a decent quality. Because this one thing to note is this this way of using a model was utilizing GPUs to the fullest. So I don't know yet what wrong I'm doing by using PyTorch tensors and embeddings, etc., and then dot modules by writing model from scratch. Uh, that my model isn't able to utilize the GPUs properly. But yeah, so this model, fully PyTorch one, was able to train faster, even with a bigger scaled up model, and generate a decent generation, uh, which so here you can see all of the three different data sets that I trained it with. Polgram essay generation. Let's read something. And so the seed of the computations happening on your desktop computer, you can often tell a good language when they before they can you a book respond and wants you to divide into. So something language is sensible, not there are obviously major blunders that are happening here, but yeah, it's able to make words, paragraphs. The character looks like polgrams, essays, etc. Python code generation is not as well. I think my input data wasn't so good, so I'll try to improve this further if I get time to build upon it. But yeah, so these generations were coming from the fully PyTorch models, LST model that I built. But for learning purposes, it would be great to go through these classes in LSTM from scratch folder. So I would be um, this particular file. I'll be copying the code from this thing to the from scratch model, and that could be referred. So yeah, I'll it was pretty easy to train a LSTM model within an half an hour or an hour maximum, a decent size LSTM model, and get some sensible results out of it. You can scale it up further to see how further good quality you can go to. So thank you for listening into the video, and um, I'll be probably stopping any further development of videos on the LSTM or RNN series now, and we'll be moving along to GPT-2, building a GPT-2 kind of model for uh, text generation. Thank you. Bye bye.